So we have to complete it with your fluid dynamics, Bernoulli's theorem, Venturi meter, and their applications. I hope so, isn't it? Okay. Let's try to start with your viscosity chapter, beta. Viscous force. Viscosity, beta. See, beta, this topic is generally because of your very small importance and one or two formulas are only there. Direct applications we need to remember for your examination. Okay. So the first point in this one, what you need to remember is viscosity is due to cohesive force mainly. Okay. Viscosity is due to what, beta? Cohesive force. Cohesive force means force due to the similar molecules. Adhesive force means force due to the different molecules. Okay, that means attractive in nature, I can say, or attractive forces. Okay, so viscosity is arising due to what forces, beta? Cohesive forces, or we can say your attractive forces. So in this one, the first formula what we need to remember is Newton's law. Newton's law. Okay, Newton's law says that the viscous nature of any liquid, now viscosity is mainly depending upon the area of cross section and also the velocity gradient. Like say if you might have been seeing the flow of your honey, the moment honey has been flowing on the surface of water, the lower part of the honey will try to stick to the ground. The upper part of the honey slowly moves in the front direction. There is some resistive force acting in the backward direction. That resistive force only we are calling it as of what? Viscous force. Exactly something like in mechanics we talk about friction. The same thing, the friction between two molecules in a water molecule and the liquid is called as of your viscous force. Okay, so I can say that in this one, viscous force Fv. I'm writing here, viscous force is directly proportional to area of contact, and viscous force is directly proportional to your velocity gradient, that is nothing but dv by dx. A is your area of cross section, beta. A is your area of your cross section, and dv by dx is nothing but your velocity gradient. Velocity gradient. Combining these two equations, we will be writing F viscous force is proportional to your area of cross section into your dv by your dx. Viscous force generally acts in which direction, beta? Opposite direction. So we write the sign with the negative sign. Removing this proportionality constant, I can write this one as F viscous force is equals to minus of neta into A into your dv divided by dx. So this is the first formula in the viscosity which you need to remember. F viscous is equals to minus of neta A into dv by dx. Negative sign indicates that viscous force is opposite to the motion of your liquid. Negative sign indicates that viscous force Fv is opposite to the motion of liquid. Beta? And what is neta, beta? This constant is known as of your coefficient of viscosity. coefficient of your what? Viscosity. How do you calculate this coefficient of viscosity? Bring the neta out. Neta is equals to your F viscous divided by your, this will be your A into your dV divided by your dx. Minus sign indicates only direction better. Is that clear? Is that clear? Okay. So and you can write even like this here. Viscous force divided by area of cross section is also equal to your neta into your dV divided by your dx. Okay, this viscous force by your area is also called as of your shearing stress. Shearing stress is equals to neta into your dV divided by dx. See it once again, beta. Viscous force is nothing but force existing between any two liquid molecules. Is called as of your viscous force. Okay, it is something like a friction which always acts in the opposite direction. Newton told that viscous force is directly proportional to the area of contact and directly proportional to the velocity of gradient. Removing the proportionality constant, we are getting a constant known as of a neta. We call that neta as coefficient of viscosity, and along with that one negative sign. Negative sign indicates that if the motion of the liquid is in positive x-axis, viscous force will be acting in the negative x-axis. Clear? So Fv by your A is equals to neta into your dV by dx. Clear, beta? Sure. Let me write the units of this one. Units of coefficient of viscosity. Okay. So I'm talking about your SI unit. SI unit is 1 Newton meter square second. Will be equal to your 1 Pascal second. That is also called as of your 1 Poiseuille. 1 Poiseuille. 1 Newton meter square second is also called as 1 Pascal second, that is equals to 1 Poiseuille. SI unit of coefficient of viscosity is Poiseuille. Whereas if I am going for your CGS unit of this one, CGS unit is 1 dyne per centimeter square. Okay, 1 dyne centimeter second. So let me talk about here what I'm getting right now. Neta is your force, Newton meter square. See here, neta is equals to your, I'm writing here, this one is Newton divided by area is your meter square. Velocity is your meter per second into distance is again meter. This one and this one will get cancelled. So this will be Newton second here and it will be your meter square. Okay, so Newton meter inverse, that is the reason Newton meter inverse second or Newton centimeter square second. That is also called as of your 1 poise. Clear, beta? And 1 Pascal second is equals to 10 poise. Beta. Yeah. Clear? 1 Pascal second is equals to 10 poise. Can anyone tell me how I got that Pascal or 10 poise, beta? 1 Newton is equals to how much, beta? 1 Newton is equals to how much? Nandini? Anyone? How many times 1 Newton is equals to? No one? Nandini Jappala. 10 power 5, very good. 10 power 5, what? Dynes. 1 Newton is equals to 10 to the power of 5 dynes. 1 meter is equals to 100 centimeters. Clear? 1 Newton is equals to 10 to the power of 5 dyne, or else I can say that 1 dyne is equals to 10 to the power of minus 5 Newton, not Pascal. Clear, beta? So 1 meter square means 10 to the power of 4 minus, that is the reason we are getting 10 points. Clear beta? Is that clear? 1 Pascal is equals 1 Pascal second is equals to 10 poise. 1 Pascal means 1 Newton meter inverse square. Do I need to do the proof? I hope you got it. Chalo, very good. Next Saturday. Coefficient of kinematic viscosity. Coefficient of your kinematic viscosity. See here, coefficient of your kinematic viscosity is represented by your neta beta. It is represented by, let us say, for example, some mu. Okay, mu is equals to the ratio of your coefficient of viscosity divided by your density. Divided by your density is known as of your coefficient of your kinematic viscosity. Mu is equals to neta divided by your rho. Units for this one is Newton per meter square. This one is your second divided by your density is mass by volume. So it is your kg, and here it will become for me meter cube. So this square and this cube will get cancelled. So this will be equal to how much will be Newton second meter divided by your kg. Okay, 1 Newton is equal to how much beta? Kg meter per second square. This is second, this is meter divided by your kg. This kg will get cancelled, second, and this square will get cancelled. Meter into meter, this will become for me meter square divided by second. That means this will be meter square second inverse. This will be the answer for this unit. Okay, in CGS unit, if I am writing in CGS system, centimeter square per second. 1 centimeter per square per second is known as of your 1 Stokes beta. Very important conversion. Therefore, I can write here 1 meter square per second is equals to 10 to the power of 4 centimeter square per second, or 10 to the power of your 4 Stokes. Got an idea? 1 centimeter square per second is 1 Stokes beta. 1 meter square means 10 in the centimeters, 10 to the power of 2 whole square. That means 10 to the power of 4 centimeter square per second. 10 to the power of 4 centimeter square second is also called as of your stroke. That means I can write this one as of your 10 to the power of your 4 strokes. I'll write here, otherwise will get it. That is 10 to the power of your 4 strokes. Done, beta? Clear? We'll be getting theoretical questions on this one beta. That's it. Okay. The next slide reading. Effect of temperature on your viscosity. Okay, very important beta. So many times asked in your competitive examination this topic. Effect of temperature on your viscosity. See here. In case of liquids beta, viscosity is due to the cohesive force of attraction, and hence when the temperature increases, viscosity of liquid will decrease. So due to the decrease in the cohesive force. Clear for everyone? So I can write here, when temperature increases, when temperature increases, viscosity of liquid decreases because cohesive force decreases. Okay, this is for your liquids. For your liquids. In gases beta, viscosity is exchanging the momentum, isn't it? And hence if the temperature increases, viscosity of your gases will be increasing. This is your viscosity of your liquid. Right here, viscosity of your liquid. You can say here right now, when temperature increases, viscosity of your gases also increases. Why beta? Due to increase in change in momentum. Important points. When temperature increases, viscosity of liquid decreases because cohesive force decreases. Whereas when temperature increases, viscosity of the gases increases due to the exchange in your momentum. Clear? Clear, beta? Sure. Next one is Stokes Law and terminal velocity. Stokes is the name of a scientist, beta. So what the Stokes told is, for any spherical body of radius r beta, when it is moving with a certain velocity in a viscous medium, like say liquid, isn't it? Viscous force is found to be directly proportional to the viscosity, radius of the spherical body, and also the velocity of the given condition. So as per the Stokes law, the formula which you need to remember is viscous force is equals to your 6 pi neta r into your V. Applicable only for spherical bodies. Applicable only for spherical bodies. Only for your spherical bodies. Important formula beta. Viscous force is equals to 6 pi neta r into your V. Okay, like see when a spherical drop is being moving in a liquid, in some liquid, water or maybe any glycerin or anything basically. One thing is, weight of this liquid no doubt acts in the downward direction. Velocity of this body is moving in the downward direction V. Viscous force is right now on this body, or from all the surfaces, viscous force acts in the upward direction. This viscous force is 6 pi neta r into your velocity. Okay, and the radius of this one is nothing but equal to your r. Okay, and along with that one, there is one more force which has been acting as it is moving in a liquid. What is that force, beta? Buoyant force. So this buoyant force will be moving in the upward direction. Okay, Fv is equals to 6 pi neta r into V, applicable only for your spherical bodies. Weight of the body acts in the downward direction, buoyant force acts in the upward direction, and viscous force is acting in the upward direction. Okay, is that clear, beta? Is that clear? Density of this body, I'm taking it as of your rho, and density of the liquid, I'm taking it as of your sigma beta. Rho is equals to your density of body. Okay, and sigma, I'm representing the density of your liquid. Okay, and in this one beta, density will be greater than of your sigma, then only the body can move in the downward direction. Okay, so as it is been dropped, when it is been dropped, initial velocity will be equal to 0. But tell me what all forces will be acting on this one beta? I'm writing here, see, forces acting on sphere. Tell me what are the forces? Number one, weight of the body mg in the downward direction. Number two, buoyant force in the upward direction. Number three, viscous force Fv acting in the upward direction as it is sinking. Isn't? Now tell me what is the net force beta? Mg in the downward direction minus upward force. Isn't it? So the net force I can write here. Therefore, net force on it is mg in the downward direction minus buoyant force in the upward direction, viscous force in the upward direction, that must be equal to mass into acceleration. Okay, so as the sphere is moving down beta, its acceleration is in the downward direction, velocity will be in the upward direction, viscous force will be in the upward direction part of relation, acceleration will be in the downward direction, isn't it? As sphere moves down, okay, its velocity will be in which direction beta? its viscous force will be in the upward direction. Acceleration will be in downward direction, like this. Okay, that will be the basic condition you need to remember. Clear? Now see. Now this body, if it is been falling with a certain constant velocity, okay, like say at certain instant, body gets constant velocity called as terminal velocity vt, then acceleration will become zero. Because if the body has been dropping in a very huge liquid column, then initially it will be accelerating, but after a certain interval of a time, the body will get a constant velocity beta. That constant velocity only we are calling it as of what? Terminal velocity. We are calling it as of your terminal velocity. This is a constant velocity, so acceleration will become zero. Now in above equation, you take acceleration to be zero beta. So what I can write here, mg minus of your F buoyant force plus of your F viscous force will be equal to your zero. Clear beta? Is that clear? So I can write here right now the equation mg will be equal to your buoyant force plus of your viscous force. Mass of the body is spherical, so mass is equal to volume into density. So 4 by 3 pi into r cube. Mass is equal to volume into density of the body is rho into your g is equals to buoyant force is equals to volume of the body totally mass 4 by 3 pi r cube, density of liquid sigma into g, plus viscous force is nothing but 6 pi neta r into this velocity is your terminal velocity, isn't it? So now if I'm simplifying this relation, all the sigma terms and radius terms I'll take on one side. So viscous force, if I'm bringing out 6 pi neta r into terminal velocity, that will be equal to your 4 by 3 pi into r cube common. G is also your common. This will be rho minus sigma because rho is greater than the density of your liquid. Clear beta? Is that clear? What's here? 2 2s are 2 3s are 3 and 3, this will become for me 9. So this pi and this pi will get cancelled. This r and this r will get cancelled. This will be square. So here it will become right now for me 9 in neta. This velocity will be terminal velocity. That is equals to 2 into your r square into g into rho minus of your sigma. Clear? So terminal velocity is how much for me beta? Vt will be equal to your 2 by 9 into your r square divided by neta into rho minus sigma into g. So this is your terminal velocity formula. Vt is equals to your 2 by 9 r square divided by neta rho minus of your sigma into your g. That means I can say that terminal velocity is directly proportional to your r square rho minus of your sigma divided by your neta, isn't it? That means as the density of liquid changes, terminal velocity changes because the viscosity is changing, and even if the body has been changing because radius changes, so velocity is also changing. So therefore I can say that terminal velocity is directly proportional to the radius. This is an important relation we need to remember. Clear beta? So terminal velocity is 2 by 9 r square divided by neta into rho minus sigma into g. Our terminal velocity will be directly proportional to your r square. Is that clear? That means if I'm drawing a graph of your terminal velocity versus your distance graph or time graph beta, one and the same. Initially it will be having constant acceleration, then afterwards it will become constant. Initially it will be increasing, velocity increases, and after a certain interval of a time it will be getting a constant velocity. That constant velocity only we are calling it as what? Terminal velocity. Is that clear beta? Is that clear? Sure. Now this is something very important for your competitive examinations beta. Note. First one, terminal velocity Vt is directly proportional to your r square. terminal velocity is directly proportional to your r square, where r is your radius. Okay. Number 2. Terminal velocity Vt is directly proportional to your A. A is nothing but of your surface area. Because area is equals to 4 pi into your r square. So area is directly proportional to r square. So I can say terminal velocity is also directly proportional to the surface area. The next one is terminal velocity Vt is directly proportional to mass to the power of 2 by 3. Mass to the power of 2 by 3. Can anyone tell me why, beta? Because see, mass is equals to, I can write as volume into density. Mass is equals to, volume is 4 by 3 pi into r cube into rho. 4 by 3 is a constant, rho is a constant, so mass is directly proportional to r cube. That means r will be proportional to mass to the power of 1 by 3. That means r square will be proportional to your mass to the power of 2 by 3. So r square is directly proportional to your 2 by 3. Here m is nothing but what, beta? Mass. Clear for everyone? Important relation. Same way, your terminal velocity Vt is directly proportional to your p to the power of 2 by 3, where p is your momentum. How I got this one, beta? Can anyone tell me? How I got this one? As momentum is equals to mass into your velocity. So that means momentum is directly proportional to mass, means directly proportional to what, beta? R cube. Velocity is directly proportional to your r square. That means I can say that momentum is directly proportional to r to the power of 5. That means r is directly proportional to the momentum to the power of 1 by 5. So therefore, r square is directly proportional to your p to the power of 2 by 5. So that is the reason I have written terminal velocity is directly proportional to the momentum to the power of your 2 by 5. Clear, beta? Then fifth one also you'll write once. Terminal velocity Vt. Vt is directly proportional to your kinetic energy to the power of 2 by 7. Terminal velocity is directly proportional to your 2 to the power of your 7. See how I got this one. Kinetic energy is equals to what, beta? Half into m into v square. That means I can say kinetic energy is directly proportional to m into your v square, beta. That means kinetic energy is directly proportional to mass is directly proportional to r cube. Velocity is directly proportional to r square to whole square. That means it is proportional to your r cube r to the power of 4. That means it is directly proportional to the r to the power of 7. So kinetic energy is directly proportional to the r to the power of 7. That means r is proportional to your kinetic energy to the power of 1 by 7. So therefore, r square is directly proportional to your kinetic energy to the power of 2 by 7. That is the reason I got here terminal velocity is directly proportional to your kinetic energy to the power of 2 by 7. Is that clear? Is that clear? Once again, everyone, these conversions are really important, beta. Terminal velocity is directly proportional to your r square. This one is your r square. Directly proportional to your r square. R is your radius. Directly proportional to your area, surface area. Directly proportional to your mass to the power of 2 by 3. Directly proportional to the momentum to the power of 2 by 5. And directly proportional to the kinetic energy to the power of 2 by 7. Clear, beta? And one more point also I'll write here right now for viscous force. For your viscous force. Viscous force is equals to 6 pi neta r into your v. So I can say that viscous force is directly proportional to your terminal velocity to the power of 3 by 2. Clear, beta? Terminal velocity to the power of 2 by 3. Sorry, 3 by 2. Because r is directly proportional to your velocity, na beta? terminal velocity is directly proportional to r square. That means r is proportional to your terminal velocity to the power of 1 by 2. Okay, velocity is already directly proportional to your r square. So it is your terminal velocity. R means v to the power of 1 by 2 into this one is nothing but equal to your v. So that is the reason terminal velocity is to the power of 3 by 2. Is it this because here it is 1 now? So it is v to the power of 1 by 2 plus 1. So that is v to the power of your 3 by 2. That means I can say that viscous force is proportional to your terminal velocity can be written as what beta? R into your r square from this one. So I can write that viscous force is directly proportional to your r cube directly proportional to your r cube and r cube is directly proportional to your mass. So viscous force in terms of mass if is writing this is directly proportional to your r cube. How I got this one beta? Can anyone tell me? See here, if viscous force is directly proportional to the radius, this velocity is directly proportional to r square. I'm just multiplying and getting the relation. Clear? Any doubt in this one? This is very important, but students generally don't remember this one. Viscous force is directly proportional to your mass. Clear, but any doubt in this one to anyone? Is that clear? Sure. Take one question based on this one. Say I'm having n identical small drops falling through a viscous medium, each with terminal velocity, with your terminal velocity v, or coalesced means combined to form a big drop. Then the terminal velocity of big drop is shall I try to do it? We are having n number of small droplets like this, n number of drops are being combining to form one bigger drop of radius capital R. Then radius is smaller, isn't these are small droplets? But how many droplets beta? N droplets are combining to form the larger droplet. That means n into volume will be remaining same 4 by 3 pi into your r cube, isn't it? Because total volume must be conserved. That will be equal to 4 by 3 pi into capital R cube. 4 by 3 will get cancelled. N into small r cube will be equal to capital R cube. That means I can write here capital R is equals to n to the power of 1 by 3 into small r. So this is the relation between capital R and small r. When n droplets are been combining to form a bigger droplet, the bigger droplet radius can be calculated with the formula capital R is equals to n to the power of 1 by 3 into small r. Now what is the terminal velocity formula beta? Terminal velocity, you know. Terminal velocity is directly proportional to your r square, isn't it? So I can write here terminal velocity of big droplet divided by your terminal velocity of your small droplet will be equal to capital R divided by your small r to the power of whole square. That means that will be equal to n to the power of 1 by 3 to the power of your 2. That means velocity of the bigger droplet will be equal to your n to the power of 2 by 3 times of the velocity of your smaller droplet. So this will be the answer for velocity of the bigger droplet will be equal to your n to the power of 2 by 3 times the velocity of the small droplet. Clear for everyone? Is that clear? Clear, beta? Terminal velocity of the bigger droplet is equals to n to the power of 2 by 3 times of the terminal velocity of the smaller droplet. See this one once. n identical small drops falling through a viscous medium, each with terminal velocity v, are coalesced to form a bigger droplet. Then terminal velocity of the bigger droplet is how much? Like say, if you are having a bucket in which you are filling the bucket with, like say 3 liters of water. That means 1 liter, 1 liter, and 1 liter must be giving you 3 liters. That means volume of the 3 liters must be equal to the volume of the individual liters. That is 1 plus 1 plus 1. Isn't it? That is the reason I am equating the volume of your n small droplets must be equal to volume of your bigger droplet. Volume of your n small drops must be equal to your volume of your big drop. Okay, that is the reason I got the relation between capital R and small r. And terminal velocity already know, directly proportional to r cube. So terminal velocity of bigger droplet divided by terminal velocity of the smaller droplet is equals to your capital R divided by small r to the power of wholes. That is n to the power of 1 by 3 whole square. So velocity of the bigger droplet is equals to n to the power of 2 by 3 times of the velocity of the smaller droplets. Clear? Sure. The next thing what you should remember in the viscosity chapter is Poiseuille's equation. Poiseuille's equation. It is used for determination of, proof is not required but for NEET, determination of viscosity of liquid. For JEE mains and advanced, we do this one in detail, but for NEET it is not required. Directly you can remember the relation, that's more than enough. Poiseuille's equation is nothing but it is used to find the coefficient of viscosity of liquid, and it is associated with your pipes, whatever the liquid is being flow. That means I can say that rate of flow is represented by Q, that is nothing but of your volume of fluid. Rate means what? Volume of the fluid divided by time. Anything divided by time is known as rate. Anything divided by length is known as what? Gradient, isn't it? So rate of this flow is given by the formula Q is equals to pi p r to the power of 4 divided by 8 neta into your L. This is the formula which you need to remember. So rate of flow of a liquid in a tube, rate of flow of a liquid in a tube, whatever the liquid is been flowing in this tube of length of your L, that is directly proportional to your pressure, directly proportional to the radius of the tube. Small r is equals to your radius of your tube. Radius of your tube. L is your length of your tube. L is your length of your tube. Clear? So Q is equals to pi p r to the power of neta into your L. Neta is coefficient of viscosity. P is your pressure. P is equals to your pressure. Clear, beta? Is that clear? That means from this one I can write the coefficient of viscosity formula. Neta will be equal to your pi p r to the power of 4 divided by 8 into Q into your L. Isn't it? This is your coefficient of viscosity relation. Clear, beta? Is that clear? Any doubt in this one? Chalo, very good. Give a small note in this one, beta. If radius of capillary tube, that means a small tube with a small hole, or a tube with a small hole. If the radius of a capillary tube increases by 10%, find percentage change in rate of flow. Percentage change in your rate of your flow. So how do you write the rate of flow, beta? Q is directly proportional to the r to the power of 4. That means I can write here Q2 divided by Q1 will be equal to your R2 divided by R1 to the power of 4, beta. So R1 here is how much for me? 100. R2 will be equal to how much, beta? 110% increase. So it is 110. So I can write here Q2 divided by your Q1 will be equal to 110 divided by 100 to the power of your 4, isn't it? So that will be equal to your how much? Can write like this one, beta? How much I'm getting? 11 into 11 is 121. 121 into 121 divided by this will become for me 100 to the power of 4. So this 10 square, isn't this 0? This 0 will get cancelled. No? So 10 square is your 100 into your again 100. Okay. So whatever you get this answer, that will be the answer condition. Okay. So this will be 121 into 121 is 14641 divided by this will become for me 10,000. So that will be approximately 1.4641. Okay, now so Q2 by Q1 will be equal to 1.4641. Okay. Now percentage is asking percentage increase in Q. How do you write, beta? Q2 divided by Q1 minus 1 into 100, that is equals to 1.4641 minus 1 into your 100. That means that will be equal to 46.41%. This is the percentage increase or change in the rate of your flow. We see it once again. The radius of the capillary tube increases by 10%. Find the percentage change in the radius of the rate of your flow. Rate of flow is directly proportional to R to the power of 4. So Q2 by Q1 is equals to R2 by R1 to the power of 4. 11 into 11 is 121 into 121 divided by 100 into 100. Just simplify it, we'll get the answer for this one. Clear, beta? Is that clear? Sure. Next one is comparison of fluid dynamics. Fluid dynamics with current electricity. Comparison of your fluid dynamics with your current electricity. First one is here I'm writing current electricity part. And this side I'm writing about your fluids. Okay. So let me take the first point in this one. You know that how the current flows, beta? Rate of flow of your charge. So charge flowing in a conductor is due to what, beta? Potential difference. First point, charge flows in a conductor. In a conductor due to potential difference. Due to potential difference. The same way in the fluid. Fluid flows. Can anyone tell me? Flows. That means volume. Due to what? Pressure difference. If there is no pressure difference, there is no flow of your liquid. Number 2. How do you write the current, beta? Current is represented by I. I is equals to your dq divided by dt. Isn't it? So when there is a flow of your current in a wire, like say this is a small wire, this is a terminal A and this is your terminal B, and there is a flow of your current in this one. So I can write here potential at your A minus potential at your B is equals to. How do you write that one, beta? Potential at your A, V is equals to your I into your R. Isn't it? Potential difference between them will be equal to how much, beta? I into your R part deflation. That is nothing but VA minus VB is nothing but what, beta? Potential difference. There is a flow of a current because of the potential difference, because this is connected to positive terminal and this is connected to negative terminal. So this is at your higher potential and B is at your lower potential. Whereas here fluid current is due to fluid current is equals to rate of flow. rate of your flow. That is Q is equals to volume divided by time. That is pi p r to the power of 4 divided by 8 neta into your L. Okay. Then third point in the current electricity, resistance. You know the resistance in the current. How do you calculate, beta? Ohm's law. V is equals to I into R. So resistance will be equal to your V divided by your I. Okay. Now how do you write the resistance? But actual formula R is equals to rho into L divided by your A, where rho is known as what, beta? Specific resistance. Isn't it? So in the same way, third point, if I'm writing here, fluid resistance. Fluid resistance. Okay. Fluid resistance is nothing but of your potential means equal to pressure. Current means we are right now Q. So it will be P by Q. So it will be 8 neta into your L divided by pi R to the power of your 4. So that will be the fluid resistance. Very important formula, beta. Very, very important formula. Okay. So R is equal to 8 neta into your L divided by pi R to the power of your 4. Clear? P is what, beta? Pressure only, na? So units, if I'm writing here right now, resistance R is equals to pressure is equals to Newton per meter square. This is volume. Q is nothing but rate. Volume per second. That is meter cube per second. Clear, beta? So that will come out for me how much? Newton meter to the power of 5 second. That means Pascal second meter cube. Okay. Very important formula. R is equals to resistance of fluid. We'll be getting a lot number of problems based upon the series and parallel combination on this one only. Clear, beta? Fourth point. When resistors are in series like this one is R1, this one is R2. R effective will be equal to your R1 plus of your R2. Fourth point. When two tubes are in series combination right now like this, and one more tube here right now. This is L1, this is your L2. Okay. So pressures, if I'm taking right now, the pressure differences must be. In this one, there will be a potential difference, beta. Here there will be V1 and here this will be V2. And here also there will be a pressure difference. So here the pressure difference will be equal to your P1 at this point and P2 at this point. Clear, beta? So here also I can write here R effective will be equal to your R1 plus R2. And you know how to write the value of R, beta? So R value is equal to 8 neta pi divided by pi and neta L divided by pi into your R. Clear? Then fifth point. When resistors are in parallel combination like this, there is division of current. The current enters here. There is a current I1 here and there is a current I2 here. Here there will be the potential same and here also there will be the potential same. This is a resistance R1, this is a resistance R2. So 1 by R in parallel will be equal to 1 by R1 plus 1 by R2. That means for the two resistors, R in parallel will be equal to your R1 into R2 divided by R1 plus of your R2. In the same way, when the two tubes are in the parallel combination like this. And the liquid is entering from here, like say Q. It will get divided here, Q1, and here it gets divided into Q2. Okay, so here there is a pipe and this one is also pipe. Again, the rate which is coming out is nothing but Q. So total rate will be here right now, Q1 plus Q2. Okay, clear, beta? Is that clear? So resistance of the wire R1 will be equal to your pi neta R na, so not pi, it will be What is R beta? See here, R is equals to your 8 neta. So it will be your 8, sorry. It will be your 8 neta L1 divided by 8 neta L1 divided by pi R1 to the power of 4. In the same way, R2. R2 is equals to your 8 neta L2 divided by pi into your R2 to the power of your 4. Okay. In parallel combination, pressure will be same beta. P1 will be equal to your P2. Isn't it? And here in this one, in the series combination, pressure will be equal to your P is equals to P1 plus P2. But rate of flow will be same. Q1 will be equal to Q2. Here potential will be equal to V1 plus V2. Clear? So once I know the values of your R1 and R2, we can substitute and simplify the relations further. Clear, beta? These are the basic things you need to remember in the viscosity chapter. Immediately what you do is you please try to complete the PYQs based on this one. You get a lot of theoretical questions based on them, especially on this part relation beta. Unit conversions and on this point. When the temperature increases, coefficient of the liquid decreases, and when the temperature increases, coefficient of the gases will be increasing. So due to the change in momentum, and the above one is due to the cohesive force decrease in the liquid part of relation. Clear, beta? Sure. Stokes law, 6 pi neta R into V, where rho is the density of the body, sigma is the density of liquid. So you need to remember this relation and try to simplify this one. Remember the formula, Vt is equals to 2 by 9 R square divided by neta into rho minus sigma into your G. So terminal velocity is directly proportional to your R square. Now these all derivations I did it. These are all of them are very important, and try to write even this one very important better. Viscous force is directly proportional to mass. Our viscous force is directly proportional to your R cube. Our viscous force is directly proportional to terminal velocity to the power of your 3 by 2. Then what is the relation between capital R and small r when small droplets are been combining to form a bigger droplet? Means capital R is equals to n to the power of 1 by 3 into your small r. And terminal velocity is directly proportional to R cube. So terminal velocity of the bigger droplet will be equal to n to the power of 2 by 3 times of the terminal velocity of the smaller droplet. And next one is Poiseuille's equation. It is used for the determination of coefficient of viscosity of liquid. The rate of flow is given by the formula volume of the fluid divided by time. So Q is equals to pi p r to the power of 4 divided by 8 neta into L. R is radius of the tube, L is the length of the tube, and P is your pressure. Okay. Then this is one small problem I have taken. You just do it out. Comparison with this one, fluids in this one. You need to remember the formula for your resistance in the series and parallel part. Fluid resistance formula 8 neta L divided by pi r to the power of your 4. So I have written this one, pi r to the power of your 4. So this one is r to the power of your 4. Okay. So in parallel combination, it is R1 plus R2. And in the series combination, it is your R1 plus of your R2. Okay. And then pressure in the series prominence will be P1 plus of your P2. Whereas in the parallel combination, the pressure will be the same, but rate of flow will be Q1 plus of your Q2 part of relation. Clear? So these are the things you need to remember in your coefficient of your viscosity. Okay, beta. So tomorrow we'll try to start with your surface tension, and today I'll try to send you some assignments on your viscosity. Please try to complete them. Okay? Sure. Take care, beta. Bye.